Hello, I'm Dr. Jacob Hudis. In this video, I'll answer the question, what is flux?
Wow, just wow, this is a dream come true.
Grasping what physicists mean by flux is crucial for understanding the fundamental laws of electrodynamics. It's an essential yet often confusing concept that helps explain the forces shaping our world. In this video, I'll break flux down and make it clear. Throughout this presentation, I'll use AI-generated voices to add a fun element and make it more entertaining.
Some of the fundamental laws in physics, like Faraday's and Gauss's laws, rely on quantifying how much of a field passes through a surface.
In physics, understanding how much field passes through a certain surface ends up being an important concept, and it's something that you need to know about if you study physics. Why can't you directly measure the field leaving every point on a surface and just sum it all up? That would give you a value for the total field leaving the surface.
Directly measuring the field at every point on a surface is impractical.
So we use the concept of flux to simplify this.
If I wanted to know how much field was leaving this surface, I could draw many points on the surface and calculate the field leaving the surface at each one of these points. And I could sum that all up. The problem is there's an infinite number of points that I've left off. There's a point here and a point here and a point here and a point here. And so this would be an unreasonable way to calculate the field leaving this surface. So what is the solution? Calculating the flux is the solution.
To calculate total magnetic flux through a surface, we divide it into small patches, multiply each patch's area by the perpendicular field component, and sum these values. This method captures the interaction between the field and the entire surface,
providing a clear measure of the field passing through.
Flux is essential in physics because it measures how much of a field passes through a given surface. This concept is foundational in Faraday's and Gauss's law, helping us compare field strengths across different areas. Flux has units of field multiplied by area. That's part of what makes all this a little bit confusing. Let's go on to the next slide where I show you how to calculate flux. This is the formula to calculate flux. In this case, it's magnetic flux. The formula is the field vector, and you take the dot product of that with the area vector. And in physics, the area vector is defined as a vector which is perpendicular to an area that you're interested in discussing. As an example, this is a circle. The circle has some area, pi r squared. The area vector is perpendicular to the area. The length or the magnitude of the area vector is the same value as the area of the surface. That's the definition of how an area vector works in physics. To calculate the flux, we multiply the field strength B by the area A of the surface. But the key idea is that it's a dot product. Only the component of the field perpendicular to the surface counts towards the flux. This gives us a consistent way to measure the amount of field actually passing through the surface. So imagine this is a surface, this is the area vector, this is the magnetic field vector. The magnetic field vector is made out of some component which is parallel to the surface and some component which is perpendicular or pierces the surface. If the field is parallel to the surface, it just skims across and doesn't contribute to the flux. Only the field lines piercing directly through the surface area count. This perpendicular component is what we define as how much field is passing through.
Electric field lines don't flow like water, but we can think of flux as a measure of how much of the field interacts with a surface. Imagine water passing through surface 1 and surface 2 in this diagram. The amount that goes in must come out, as long as the surfaces enclose the same field lines. But remember, the analogy has limits. Unlike water, the electric field is everywhere on both surfaces simultaneously.
What exactly do you mean by flux interacts with the surface?
It means that the flux depends not only on the field strength, but also on the surface orientation. The way the surface faces the field affects the flux value.
Is the flux capacitor real?
Nincompoop.
What the flux does this even mean?
Fair reaction. Just think of flux as a way to count how much of the field touches a surface. We'll keep working through examples to make it clearer.
Here's surface 1 and surface 2. Imagine you're squirting water through a surface, which we'll call surface 1. To calculate the water flux, we can break down surface 1 into many small area elements. For each element, we calculate the amount of water passing per unit time and multiply it by the area. This gives us the contribution of each element to the total flux. However much water passes through surface 1 will eventually pass through surface 2. To calculate the flux for surface 2, we use the same process. Here's the interesting part. Surface 2 has a larger total area than surface 1. For surface 2, the flow rate per area element is smaller, so when we sum up all these elements, the total flux remains the same for both surfaces. These analogies help make complex ideas easier to grasp. Physics is full of these useful, yet limited analogies. Finally, I want to discuss that flux can change in one of three ways. Flux is equal to B times A times cosine of theta. Let's focus on the left first. The field changes strength. If I change the field strength, you can see that the flux will change because the magnetic field is changing. The area stays the same and the cosine of theta stays the same, but the magnetic field changes, and in this case the magnetic field gets weaker, and so the flux decreases. Another way that you can change flux is if the loop changes shape. B will stay the same and cosine of theta will stay the same, but the area will change. In this case, the area gets smaller and therefore the flux gets smaller. Another way flux can change is by changing the orientation of the area. So in this example, the magnetic field stays the same and the area stays the same, but the cosine of the angle between the area vector and the magnetic field changes. Please see my next video in the playlist where I calculate flux and solve flux example problems. Math and Physics Tutoring with Dr. Hudis.